welcome. This is the problem review for AP Calculus AB and BC, Unit 1, Limits and Continuity. We'll be going over both multiple choice questions and free response questions, both calculator active and calculator inactive. Let's get on to our first problem. Alright. I don't know how well you can see that, but that says the limit as x approaches infinity, positive infinity. Alright, so let's apply the techniques we know on this fraction to find the limit as x approaches infinity. So if you remember, what we did to find limits at infinity or negative infinity is we found the highest degree term, right? So let's find the highest degree term. Well, in the numerator, in both the numerator and the denominator, we are multiplying two polynomials. In the numerator, the highest degree in the first polynomial is 2x, or 1, and then the highest degree in the second polynomial is 1 in the form of negative x. If we multiply that together, we get that our highest degree polynomial in the first fraction is negative 2x squared. And we could multiply all that out, but if you look at it, there's just no other way to get a degree that's 2 or higher. So we really don't care about it, because we're trying to find a limit at infinity. Now looking at the bottom, in the first polynomial, the highest degree is 1. Second one, the highest degree is 1. So we have to multiply those two together, and we get x squared. Now, since these are the same degree, we find the limit at infinity by dividing the coefficients. So this will just end up being minus 2 over 1, or minus 2. Therefore, our answer here is B, minus 2. Let's look at another problem. So right now, we are in calculator inactive problems. Now this says x as x approaches 0, and this is 5x fourth plus 8x squared over 3x fourth minus 16. Sorry for the poor resolution, but yeah. And then let's see what we can do with this. So if you remember, when we were trying to find a limit at infinity, the strategy we used, we divided everything by this highest degree term, or x to the fourth in this situation. And we ended up with a bunch of stuff like 1 over x squared. And that would come out to be 0, because 1 over infinity, it approaches 0 as infinity becomes infinity. Now we can apply the same idea here. If we have an x squared or an x or like any x term whatsoever, then when we plug in that 0, we're going to have that end up being just 0. So what we can do to this fraction, since we know if we just plug in 0 right now, we're going to get 0 over 0. That's indeterminate form, which means that we can keep going. There is an answer, but we haven't found it yet. And we cannot find it just by plugging in the numbers. So what we can do here is we can divide every single thing here by the lowest degree, which is x squared. So if we divide this by x squared, well, these two go away, and the other two become x squared terms. And now if we plug in 0, well, the 5x squared, that's 0. The 3x squared is also 0. So this ends up becoming 8 over negative 16, which is negative 1/2. Now looking at our answer choices, that is answer choice A. Now notice what we did here is the same idea that we drew when we're evaluating limits at infinity, right? And very often, even if you forget a formula, you can still rederive it using this kind of strategy, just thinking about what you know before, what you've done before, and then trying to apply the same thing to a similar problem. Now with that, let's get on to our next problem. Okay. Let f be the function defined above. Which of the following statements about f are true? F has a limit at x equals 2. F is continuous at x equals 2. And f is differentiable at x equals 2. Now, since we're still in Unit 1, you probably don't know what differentiable means yet. But I'll help you walk through that when we get there. Now, first, let's see. Does f have a limit at x equals 2? Now, I hope you can see that clear enough. And I apologize for the poor resolution. Now, this is if x is not equal to 2. And, well, x squared over 4, right, this x squared over 4 term up here, we can factor that, make that x minus 2 times x plus 2. And that way, we can cancel that out, we can cancel that out. And this just becomes x plus 2. Now, if x is not equal to 2, then we have x plus 2 as our function. So as we approach x equals 2, our limit is going to be using this x equals 2 function. So let's plug in 2 into here, and we get 2 plus 2 equals 4. Now, this is not our actual value at x equals 2. Keep that in mind. This is the limit as x approaches 2, right? So the limit as x approaches 2. Well, that means that f does have a limit as x equals 2. We can put a 4 right there. Now we need to see if it's continuous. Now, remember from our content review video that continuity occurs when you have a value of f equals x, a value of the limit of f equals x, and when the limit and the value are equal. So we have a value of the limit. We have a value of the actual function. If x equals 2, we get 1. So we do have a value of that. Now I have to find out for continuity if this limit is equal to the value. And you can pretty clearly see it's not, because 4 is not equal to 1. So this one does not work. It's not continuous. And now we get to differentiable. So you probably don't know what differentiable means yet, but in the case of this problem, it doesn't really matter, because one important thing you should know is that if something's not continuous, it's definitely not differentiable. So if it's not continuous, it is not differentiable either. So we can just cross that out. So 1 is the only one that works. So our answer is A. Let's get on to the next problem. For x is greater than or equal to 0, the horizontal line y equals 2 is an asymptote for the function f. Which of the following statements must be true? Okay, so all they really give us in information is that y equals 2 is an asymptote for all positive values of x. And so let's think about what an asymptote really means. An asymptote means that as x approaches infinity, positive infinity in this case, so they're telling us greater than 0, greater than or equal to 0, then as x approaches infinity, y approaches 2. So what can we see? Well, we just said out loud kind of gives us the answer, right? Let's look at answer choice E. As the limit as x approaches infinity is 2. That's basically what we just wrote down, right? As x approaches infinity, y is 2. And you should remember this. That's the definition of a horizontal asymptote. As x approaches infinity or negative infinity, y approaches the value of that asymptote, of the horizontal asymptote. Therefore, E is our answer. Let's get to our next problem. You probably don't want to see me just clicking through this a bunch of times, but apologize for that. All right, let's look at this. Another limit at infinity. So Well, we know how to handle limits at infinity anymore now, right? All we have to do is look at the highest degree term. So in essence, we can just forget that these terms exist. They're gone. They don't exist anymore. We just have an x cubed over 4x cubed. And, well, it's not equal to, but as we divide the coefficients out, we get 1 over 4. And that was a quick one, but looking at answer choices, we're done with that one. Alright, let's get into our last question of the MCQ section. And now the last couple questions have been calculator active, but as you can see, we haven't really needed to use a calculator, so we just didn't use it. Of course, you will need to use a calculator in some calculator active problems going forward, but in this unit especially, there's really nothing that requires the use of the calculator. But yeah, let's see what we have here in this question. Which of the following does the limit as x approaches 4 exist? So one is there's a curve, there's a curve, and there is a hole right here. So it's not continuous, but that's not what they asked us for, right? All they asked us for was, does the limit exist? And, well, as you approach from the left-hand side, go to there, that point. As you approach from the right-hand side, you go to that same point. So while the function is not defined at this point right here, that's the limit. The limit does exist. This one works. Let's see the next one. Well, it has basically the same structure, right? As you go from the left-hand side, you approach that point. As you go from the right-hand side, you approach that point. So that one point is the limit, and this one works. And in general, if you see removable discontinuities like that whole same thing over here with that hole, you generally will have the limit existing. On the other hand, let's look at this third one. Let's look at jump discontinuities, right? Now, it's called that, obviously, because it goes like this, and then it jumps down here, right? Now, if you look at it, from the left-hand side, the limit is this value. From the right-hand side, the limit is this value. These values aren't the same, so there is no limit. If you have just jump discontinuities, generally you will not have a limit because the limit from the left-hand side will be different. It'll jump from the limit of the right-hand side. So therefore 1 and 2 work and 3 doesn't. Looking at answer choices, that is choice D. Let us move on to some free response questions. Now, I hope you enjoyed this video. I hope you found it informative and that you learned something. And if so, I'll see you next time.